In applied mathematics, the Joukowsky transform, named after Nikolai Zhukovsky, who published it in 1910, is a conformal map historically used to understand some principles of airfoil design. The transform is z equals zeta plus 1 zeta, display style z equals zeta plus frac 1 zeta, where z equals x plus I y, display style z equals x plus I y, is a complex variable in the new space, and zeta equals chi plus I eta, display style zeta equals chi plus I eta, is a complex variable in the original space. This transform is also called the Joukowsky transformation, the Joukowsky transform, the Joukowsky transform, and other variations. In aerodynamics, the transform is used to solve for the two-dimensional potential flow around a class of airfoils, known as Joukowsky airfoils. A Joukowsky airfoil is generated in the complex plane z, display style z, plane by applying the Joukowsky transform to a circle in the zeta, display style zeta, plane. The coordinates of the center of the circle are variables, and varying them modifies the shape of the resulting airfoil. The circle encloses the point zeta equals -1, display style zeta equals -1, where the derivative is 0, and intersects the point zeta equals 1, display style zeta equals 1. This can be achieved for any allowable center position mu x plus I mu y, display style mu underscore x plus I mu underscore y, by varying the radius of the circle. Joukowsky airfoils have a cusp at their trailing edge, a closely related conformal mapping. The Kármán-Trefts transform generates the much broader class of Kármán-Trefts airfoils by controlling the trailing edge angle. When a trailing edge angle of 0 is specified, the Kármán-Trefts transform reduces to the Joukowsky transform. Monsieur General Joukowsky transform. The Joukowsky transform of any complex number zeta, display style zeta, 2 z, display style z, is as follows: z equals x plus I y equals zeta plus 1 zeta equals chi plus I eta plus 1 chi plus I eta equals chi plus I eta plus chi minus I eta chi 2 plus eta 2 equals chi 2 plus eta 2 plus 1 chi 2 plus eta 2 plus I eta chi 2 plus eta 2 minus 1 chi 2 plus eta 2. Display style begin aligned z and equals x plus I y equals zeta plus frac 1 zeta and equals chi plus I eta plus frac 1 chi plus I eta and equals chi plus I eta plus frac chi I eta. Chi caret 2 plus eta caret 2 and equals frac chi. Chi caret 2 plus eta caret 2 plus 1. Chi caret 2 plus eta caret 2 plus I frac eta. Chi caret 2 plus eta caret 2 minus 1. Chi caret 2 plus eta caret 2 end aligned. So the real x, display style x, and imaginary y, display style y, components are x equals chi 2 plus eta 2 plus 1 chi 2 plus eta 2 y equals eta chi 2 plus eta 2 minus 1 chi 2 plus eta 2. Display style begin aligned x and equals frac chi caret 2 plus eta caret 2 plus 1 chi caret 2 plus eta caret 2 y and equals frac eta chi caret 2 plus eta caret 2 minus 1 chi caret 2 plus eta caret 2 end aligned. Sample Joukowsky airfoil. The transformation of all complex numbers on the unit circle is a special case. Pipe zeta pipe equals chi 2 plus eta 2 equals 1, which gives chi 2 plus eta 2 equals 1. Display style zeta equals sqrt chi caret 2 plus eta caret 2 equals 1 quad text, which gives quad chi caret 2 plus eta caret 2 equals 1. So the real component becomes x equals chi 1 plus 1 equals 2 chi. Display style x equals frac chi 1 plus 1 equals 2 chi, and the imaginary component becomes y equals eta 1 minus 1 equals 0. Display style y equals frac eta 1 to 1 equals 0. Thus the complex unit circle maps to a flat plate on the real number line from -2 to +2. Transformation from other circles make a wide range of airfoil shapes. Velocity field and circulation for the Joukowsky airfoil. The solution to potential flow around a circular cylinder is analytic and well known. It is the superposition of uniform flow, a doublet, and a vortex. The complex conjugate velocity W tilde equals U tilde x minus I U tilde y. Display style y de tilde W equals y de tilde U underscore x I y de tilde U underscore y. Around the circle in the zeta display style zeta plane is W tilde equals v infinity e minus I alpha plus I gamma 2 pi zeta minus mu minus v infinity r 2 e I alpha zeta minus mu 2. Display style y de tilde W equals v underscore and d e caret I alpha plus frac I gamma 2 pi zeta mu frac v underscore and d r caret 2 e caret I alpha zeta mu caret 2, where mu equals mu x plus I mu y. Display style mu equals mu underscore x plus I mu underscore y is the complex coordinate of the center of the circle. V infinity display style v underscore and d is the free stream velocity of the fluid. Alpha display style alpha is the angle of attack of the airfoil with respect to the free stream flow. R display style r is the radius of the circle, calculated using r equals 1 minus mu x 2 plus mu y 2. Display style r equals sqrt 1 mu underscore x caret 2 plus mu underscore y caret 2. Gamma display style gamma is the circulation found using the Cutter condition, which reduces in this case to gamma equals 4 pi v infinity r sin alpha plus sin minus 1 mu y r. Display style gamma equals 4 pi v underscore and d r sin left alpha plus sin caret minus 1 left frac mu underscore y r right dot closing curly bracket. The complex velocity w display style w around the airfoil in the z display style z plane is, according to the rules of conformal mapping and using the Joukowsky transformation, w equals w tilde d z d zeta equals w tilde 1 minus 1 zeta 2. Display style w equals frac y de tilde w frac dz d zeta equals frac tilde w 1 frac 1 zeta caret 2. Here w equals u x minus I u y. Display style w equals u underscore x u underscore y with u x display style u underscore x and u y display style u underscore y. The velocity components in the x display style x and y display style y directions respectively. Z equals x plus I y display style z equals x plus I y with x display style x and y display style y real valued. From this velocity, other properties of interest of the flow, such as the coefficient of pressure or lift, can be calculated. A Joukowski airfoil has a cusp at the trailing edge. The transformation is named after Russian scientist Nikolai Zhukovsky. His name has historically been romanized in a number of ways. Thus, the variation in speaking of the transform is year. Kármán-Tréfft's transform. The Kármán-Tréfft's transform is a conformal map closely related to the Joukowski transform is year. While a Joukowski airfoil has a cusp trailing edge, a Kármán-Tréfft's airfoil, which is the result of the transform of a circle in the zeta display style zeta plane to the physical z display style z plane, analog to the definition of the Joukowski airfoil, has a non-zero angle at the trailing edge between the upper and lower airfoil surface. The Kármán-Tréfft's transform therefore requires an additional parameter, the trailing edge angle alpha display style alpha. This transform is equal to z equals n b zeta plus b n plus zeta minus b n zeta plus b n minus zeta minus b n. Display style z equals nb frac zeta plus b caret n plus zeta b caret n zeta plus b caret n zeta b caret n a, where b display style b is a real constant which determines the positions where d z slash d zeta equals 0. Display style dz d zeta equals 0 and n display style n is slightly smaller than 2. The angle alpha display style alpha between the tangents of the upper and lower airfoil surface at the trailing edge is related to n display style n by alpha equals 2 pi minus n pi and n equals 2 minus alpha pi. Display style alpha equals 2 pi n pi quad text and quad n equals 2 frac alpha pi. The derivative d z slash d zeta display style dz d zeta required to compute the velocity field is equal to d z d zeta equals 4 n 2 zeta 2 minus 1 1 plus 1 zeta n 1 minus 1 zeta n 1 plus 1 zeta n minus 1 minus 1 zeta n 2. Display style frac dz d zeta equals frac 4n caret 2 zeta caret 2 minus 1 frac left 1 plus frac 1 zeta right caret n left 1 frac 1 zeta right caret n left 1 plus frac 1 zeta right caret n left 1 frac 1 zeta right caret n right caret 2. Background. First, add and subtract 2 from the Joukowsky transform. As given above, z plus 2 equals zeta plus 2 plus 1 zeta equals 1 zeta zeta plus 1 2 z minus 2 equals zeta minus 2 plus 1 zeta equals 1 zeta zeta minus 1 2. Display style begin aligned z plus 2 and equals zeta plus 2 plus frac 1 zeta equals frac 1 zeta left zeta plus 1 right caret 2 z2 and equals zeta minus 2 plus frac 1 zeta equals frac 1 zeta left zeta minus 1 right caret 2 end aligned. Dividing the left and right hand sides gives z minus 2 z plus 2 equals zeta minus 1 zeta plus 1 2. Display style frac z2 z plus 2 equals left frac zeta minus 1 zeta plus 1 right caret 2. The right hand side contains as a factor the simple second power law from potential flow theory applied at the trailing edge near zeta equals plus 1. Display style zeta equals plus 1. From conformal mapping theory, this quadratic map is known to change a half plane in the zeta display style zeta space into potential flow around a semi-infinite straight line. Further, values of the power less than 2 will result in flow around a finite angle. So, by changing the power in the Joukowsky transform to a value slightly less than 2, the result is a finite angle instead of a cusp. Replacing 2 by n display style n in the previous equation gives z minus n z plus n equals zeta minus 1 zeta plus 1 n display style frac zn z plus n equals left frac zeta minus 1 zeta plus 1 right caret n, which is the Kármán-Tréfft's transform as you're solving for z display style z gives it in the form of equation a. Symmetrical Joukowsky airfoils. In 1943, H.S.U.E. Shensian published a transform of a circle of radius a display style a into a symmetrical airfoil that depends on parameter display style epsilon and angle of inclination alpha display style alpha closing curly bracket z equals e I alpha zeta minus plus 1 zeta minus plus 2 a plus display style z equals e caret I alpha left zeta epsilon plus frac 1 zeta epsilon plus frac 2 epsilon caret 2 a plus epsilon right closing curly bracket. The parameter displaystyle epsilon yields a flat plate when 0 and a circle when infinite. Thus, it corresponds to the thickness of the airfoil. Notes: Joukowsky transform NASA applet.